Hello, welcome, and an excellent evening I wish to you. And today's episode is mostly about these things here, which are voltage regulators. This here is a 7805, a linear voltage regulator that takes some input voltage, usually between 8 and 25, 26 volts, and transforms it down to 5 volts, shedding the excess voltage mostly as heat. This thing in particular here is from 1984, 43rd week, and it's generally very reliable. I soldered this out from one of my floppy drives, either 1541 or maybe the 8050 Commodore drive. And this thing is still good. So why did I desolder it? Because there are modern replacements like this one here from EasySBC, which uses a modern switching voltage regulator that chops up the higher voltage into smaller chunks basically without dissipating so much heat. The performance of the 7805 is pretty decent, I would say. However, the 1541 and especially the 8050 with 3 voltage regulators, similar to the PET with 3 voltage regulators, do tend to run a little bit hot, especially in the summer. So you're just fine leaving these in. But for example, if you stack 2 devices, it gets already a bit problematic due to too little ventilation and stuff. There's of course also the transformer that puts out a little bit of heat, etc., etc. And sometimes you also have the problem that these eventually die. They are pretty long-lived, but sometimes they do die, and they get used in a lot of devices, a lot of old retro computers, pinball machines, stuff like that. And the 7805 is very ubiquitous, but this particular variant is not produced anymore. Only the 3-legged variant in the little plastic chip package that you can still get, but these ones not so much. So that's where things like this come in. However, people on the forums, so I've used these in 2 or 3 devices already, and they come in a 5-volt variant, also in a 12-volt variant, slightly different looking, but very similar in construction, to replace the 7812. And these basically run fine. However, someone told me to measure the output of this. I forgot at which capacitor one of these is the output capacitor, probably the one here, the 2 here on the output pin. That's where the output voltage comes out. To measure the ripple here with the oscilloscope, and we will do that in a minute. And yeah, the issue here is that the so-called ripple is actually relatively high. You have to imagine that this thing takes DC, so basically a flat voltage, and also outputs DC. But due to the switching component here, it produces noise. And that noise can go up to quite a couple of millivolts. And the usual TTL logic in these old computers can tolerate only so much ripple. The less ripple you have, the better, the more stable things should run. I didn't have any issues with this, but people say it's not good for the chips. So I'm not an electrical engineer, I'm a computer scientist, so I do roughly understand what's happening here, but I couldn't design one of these or judge if this is indeed problematic compared to the very smooth non-rippled output, because this is linearly happening, so this is just dissipating heat and lowering the voltage more or less. Not sure if that's really a problem. But one person on the DOS Reloaded forum thought, well, I can do better. And he designed this. This is the DR340 replacement voltage regulator. It's also a switching voltage regulator, but as you can see, it has many more components in the same form factor as the previous one. And this is extremely low ripple, and it's configurable for 5 or 12 volts. This is the 5 volt variant. Here with the Sharpie, the 5 volts are marked, and on the 12 volt variant there will be a 12, which I have in here. We will have a look at that in a second. It was designed by Mr. Floppy, and he even created a very nice data sheet for this with all the infos that you need, and even an example measurement of the ripple, which is almost not visible if you don't zoom in very, very far. And this is one of the prototype boards. I think the final version will not have this feature, because this one here got a teeny tiny little BNC jack for attaching your oscilloscope directly, so that you don't measure any interference from anywhere else, but only the noise that is generated by this particular component. We don't have that on here, and I guess this will get away with the production version. That being said, this is open source hardware. I have to ask around. I don't think it is yet up on any of the open source project sites, but this suggests that it eventually will be. And yeah, I hope to be able to supply you with a link. And yeah, what I want to do is to replace the 7805 and the 7812 in one of my broken 1541s, and also replace the read-write head, because that's why it's broken, at the same time. But in the meantime, we can also check the voltages that these things output using my little power supply that I got earlier this year with the nice probes here. And let's see if these things actually output or produce the voltage that they're supposed to, at least without any load attached to it, obviously. So this is our test setup. I've clamped the common lead of the multimeter to the casing of the voltage regulator, because that is ground. The left pin on the back side, if you turn it so it's slightly asymmetric, if you can see that. So the pins are on the lower half here, on both of these, and also here. So the left pin is the input, the output, and the right pin is the input. So I attached the input of my power supply onto the right pin, the positive terminal of my multimeter to the left pin, and also the ground or the common of the voltage of the power supply to the case as well. And as you can see, this 7805 produces 5.09 volts if you have no load basically on there. And I'm inputting 10 volts at the moment. I'm gonna turn it down a little bit to 8.7 and then 8.2, and now I'm at 7.4, and it goes up to 7.1 volts, but it should drop significantly soon. We're now down to 6 volts and now to 4.7, and then you only get like 3.8, 6. Well, makes sense if you don't get it. Now I have 5.6 volts and get out 4.7 volts. So it does make sense that you don't get the full 5 volts anymore, because you can't boost anything. But around 8 to 10 volts is probably a good value. And as you can see, this works fine. Let's quickly switch around to one of the other voltage regulators. I've turned off the power, obviously. So let's choose the easy SBC variant. Make sure not to destroy any components on the back side. And turn on the power supply again. and we get 5.2 volts. This is a little bit high, and this will also stay even if I go down to 7 volts or something. Yeah, but around 9 to 10 volts, it's smack on 5.2. This is a little bit high, but there's a pot that you can adjust to lower this a little bit. So, working fine as well. Turning off the power supply. And switching to the new DR voltage regulator by Mr. Floppy. Again, touching ground lead. And the voltage output. Ground lead for the power supply. And the voltage input. And turning it on. Gives us 5.092 volts on this uncalibrated multimeter. Looks good as well. Works down to roughly about 8 volts. Now I'm at 8.1, still looking good. I'm slowly going down. 7.8, 7.5. Now we're at 6.9. And we are now I'm at 6 volts and getting only 3.3 volts out of it. And I think if I go up to pretty much 8 volts, spot on. Now I'm at 7.8, but I think now it's getting probably a bit flaky. So yeah, you definitely need 8 volts. Something between 9 and 10 is probably excellent for this, so you can use 9-volt power supplies for things that use this. Looking good. We can confirm that all 3 of these do work. The question is, how much ripple do they produce, and we'll have a quick look to that as well before trying to put this new one into an actual drive. And first I want to also show you the 12-volt variant. I think the only difference is one resistor that gets switched to control one of the chips on here, one of the switching, whatever it is, regulator, I don't know. And it comes with these little tiny machined pins, and you can press them into the holes here. You need to be a little bit careful while doing that, but it's relatively easy to do, and you don't have to solder these in, but it might help for structural rigidity. And you must not push them in too far, or they will of course drop out the other side. Maybe I can more easily insert these from the top actually, but then you have to be careful not to destroy any of the components here. It's all very tiny, as you can see. The good thing is this is all SMD, and as far as I know, this came like this from the factory in China. I think this was done by JLC, so they can be produced really cheaply, basically. And this is actually not an expensive solution. Should be hopefully less than 10 euros per regulator, which is fine if you want to have your drives running especially cool and hopefully reliably. So this is the 12-volt version. As I said, you can see it here, the number with the Sharpie. Yeah, and this is the 12-volt version. Maybe we can also check this one. So let's grab the multimeter again. Putting the leads on for the output voltage. And again, well, with 10 volts, that won't do it, obviously, I guess. Except if there's a boost circuit in there. Let's see what happens. Inputting 9.5 volts and you get 9.3 out. So you probably need more than 12 volts. I'm gonna go to 17 volts here, and we get 11.99. I think that's pretty good. Going up to 20 volts, and yeah, still behaves the same. I get a little bit of fan spin on my power supply here, but yeah, seems pretty decent, seems very stable. I do have a 7812 over in my parts bin somewhere. Maybe I can pick that one up as well, but I think that looks pretty good. Turning it off takes a bit to discharge, obviously. And that is the 7812 replacement. Very nice. Let me fetch the 7812. So here's the 7812 12 volt regulator. There's also a 7905 and a 7912 delivering negative 5 volts and negative 12 volts. I think it is planned that there will be a variant that can supply minus 12 volts as well, because that's something that you need in the older machines like the PET. But at the moment it's only the 5 and 12 volt versions, which are also much more common, let's say. And the minus 12 versions usually last a lot longer, because the minus 12 volt rail is usually only used for bias voltages on old DRAMs, and that is only a couple of milliamps, so they don't have a lot of load. Also, what I wanted to show you is these variants here, the 7805 in the plastic package, is still readily available, so that's not an issue. But you can put them in this place as well, but you have to bend the legs and do a little stuff to make it fit, and it's not very nice. So these variants that are just really drop-in replacements, I think are much nicer to have. So again, attaching and taking care that the orientation is correct. Not to have the output on the input or the other way around. Then turning it on. We're getting 11.62 volts on 17.3 input. Let's go up a bit to 19. Yeah. Doesn't do much, it's pretty stable. 18 volts I'm now on, and getting out 11.62 volts. So this regulator is fine as well. This variant you usually need for, especially in the 1541, for the drive mechanism, because the motors are all 12 volt. 5 volt is usually used for the TTL logic and the CPU and similar things. But there you have it. While I do think that these things are probably pretty decent and good enough for a lot of people, it's very nice to have this replacement with the ultra low ripple. Next up we can perhaps see and measure the ripple on both the original ones, where I'm thinking that we won't see any ripple, or at most we will see stuff interference from outside, because these don't introduce any ripple. Anything that gets in here is probably from our power supply, which we can actually also measure. I think I can probably attach this these things to my probe basically and run it on 5 volts or something, and see what kind of noise this power supply actually introduces. And then we can see how the new ones deal compared to this one. So now we have the setup ready and the oscilloscope running and also zoomed in. The blue curve is the EasySPC regulator, the yellow curve is the DR regulator by Mr. Floppy, and they are both to the same scale, 200 millivolts per division, and we are feeding in 9.2 volts at the moment, getting probably 5 volts out, I would guess. Can't see that here because I haven't added that, but what you can see here is the actual ripple on the oscilloscope. The update is much smoother, and what you can already see is, even though this is a very poor measurement setup because there's noise and interference from all around, you can see the typical sawtooth pattern here, which is more prominent when you look at the actual oscilloscope screen. For example, here you can't can hardly see that, but on the fast refresh and averaging scope screen it's very visible. However, it's very clearly visible that the noise on the blue line is voltage peak to peak 350 millivolts at times. I think those are the spikes that you can see here, because we have like 200 millivolts per division. And it's much smaller, only around 80 to 100 millivolts peak to peak on the yellow. And also the apparent noise that we see here is a bit smaller. But this is, as I said, a very poor measuring method. I don't have a cable for the BNC connector, otherwise I would show you that. But what we can try and do is use the probe a bit more directly by attaching a little spring pin on the ground thingy here and trying to probe one of the components that's on the output pin. Let me try to do that. Maybe we can see a little bit the difference in quality between these two things. So here we are with a 1541 classic longboard. I think this is assembly 250442 revision A. I think this is pretty common for drives from around 1984. And yeah, this one is in good working order. The drive itself, the drive mechanism is in the background there. It has a dead read-write head, but I do have one new old stock lying around, so we'll replace that. And while we do that, we will clean up this board. It's a bit dirty. And here you can see the two voltage regulators, the 7805 and the 7812. And yeah, this we will replace with the new low noise variants. So that should give us a much cooler experience, basically, because this has a huge heat sink, as you see, and it can run quite warm. And I think this is pretty good idea to prolong this device's lifetime, probably. I mean, these voltage regulators, I will still keep them because they're still good. They are functioning within specs. But still, I like to try this on a real device. The board here has no particular things. It's still jumper to device number 8. Has two ROMs here, the CPU, the 6502, two VIA chips for interfacing, and an SRAM chip. Many of the chips here are socketed. That's very nice. Easier to replace if they fail. And I think I took the ROM from this board and put it into another drive. So I took one of my other dead drives and replaced the ROM here. So, and quickly booted it up using my external power supply here. Injected 5 volts to see if it actually comes up properly. And it does. So that's a good thing. So what we'll do now is I will remove the screws that hold down the packages here, basically, and then from the bottom side I will desolder the voltage regulators, and then we can put in the new voltage regulators and reuse the screws for the connection to the ground plane. So that's a pretty straightforward swap. Only thing you have to really make sure is that the 12 volts go on the right side and the 5 volts go on the left side. Otherwise, you probably destroy all the ICs on here, and that wouldn't be a good thing. So, desoldering was simple enough. Here we have the bare PCB now. There's still a bit of thermal compound attached there, so I will clean everything very thoroughly with some isopropyl alcohol. There are some very weird plastic thingies for isolation purposes, I guess. Not even sure they are strictly needed. I think on some of the other 1541s I do have some kind of silicone pads, so maybe they are necessary. Probably to help against shorting out against something. I'm not quite sure. But I wouldn't think, because the whole casing is ground, so I think that should be fine. Same with the heatsink here. It's pretty nasty and dirty, so I'm gonna clean all of this up, and then we can put the heatsink back in, because I want to, because it's, first of all, it's structural. There are like screw holes here that mount to the side, so it does keep the PCB in place, and I want to keep this in the machine so you can technically revert it back to original configuration, even with the very soggy 1541, 7805 and 7812. Yeah, so let's do that. A very quick interlude here. I was trying to get this drive working, and it does work on the C64. However, on my Zoom floppy interface, which is this brilliant thing here, which is a USB interface for serial and parallel Commodore drives, it wouldn't be detected, which is very weird. So I asked around in the forums, and someone said, well, maybe the pull-up resistors near the 7406 are bad, or something's wrong there. I checked everything looked fine. However, those on the 7406 are not the only ones. Here are the schematics for this board. These are the serial interfaces, which are these boards over here, and they run somewhere along these lines to these both chips. This is the 7406 and this is the 74LS14. The 74LS14 is doing some stuff here. I think it's NOT gate or something, in an inverter basically. And there's this peculiar line 3, which is the ATN line on the serial IEC bus. And there is one pull-up resistor called R5, which should have 1K, going into pin 13 of the LS14. So when I check that 1K resistor in circuit, I'm getting roughly 420 ohms, which is not good, because it should look like it's neighboring R6, which is 1 kilo ohm. And then we can desolder both legs, oh no, just one leg, one going to the 74LS, lifted one pin, and now we're getting, let's see, exactly 1K. So the resistor is good, which means the 74LS14 is bad. So what are we gonna do? We are gonna desolder that. And the thing is, I was measuring with the multimeter and the oscilloscope on pin 13, which is the input. And I could see, while it should be high because it has the pull-up resistor there, it would be only at something like 1.2 volts. So there's definitely kind of a short inside this IC, it seems, pulling it down towards ground, not completely, because the pull-up resistor is pulling against that. But yeah, so that seems to be the issue. I do have, where is it? I do have some replacement IC. This is a 74LS14 by the same company, Synetics, but somewhat newer. It's from 1987, and the one on here is from 1984. So we're just going to replace that and solder the resistor back in place, I would say. So I'm firing up the desoldering gun, and I'm going to do this very quickly. The desoldering has been completed. There's a nice socket now in there with the 74LS14 replacement. The pull-up resistor is back in, and I've got my Mini Pro here, the TL866, with the presumably damaged chip, because this one can do testing of 74 series logic chips. Not perfect, but if they are really bad, it will detect that. So let's look at that. Okay, so you can test using either the graphical user interface in Windows, or on macOS and Linux you have the Mini Pro utility that you can install using brew or apt or whatever package manager you're using. And you can select the device with -P 7414. The LS variant is with the same pinout, has different timings, but this programmer can't discern between those two. And -T, capital T, means test this specific device. And if you do that, we can see there is exactly one error, namely the output on pin 12. Input on pin 13 was high, expected was low, but we're getting an error here. So basically this thing is broken, I think. That's what this means. It's definitely corresponds to what exactly I was measuring, that pin 13 and 12 are seemingly incorrect. Not sure which is the input and what is the output. Maybe it was the other way around. Yeah, but definitely an error exactly on that pin. So good that we replaced it. Now everything we need to do is to put back together the drive and see if Zoom Floppy sees it. Okay, time to flip the switch. Everything is connected. The drive mechanism is on there. The Zoom Floppy is connected. Turning on. And nothing happens because my power strip was off. And this is looking not so good, because the drive mag was connected incorrectly. And I hope I didn't kill anything. That would be massively stupid, but things happen. So let's see. Using the CBM tools, and especially the command CBM control detect, we can see that the drive is at least detected, so the main logic board is working. We can try to do a directory, because I think I formatted this disk previously. And there we go, it definitely works. We can even try to copy something over. I think I have a demo here. D64 copy, and we will write some demo by Padua onto the disk, and we'll see if that works out fine. And there you have it. The disk has been written correctly, and I would suggest that this disk drive is officially repaired. All that's left to do is basically to show you a little bit that I can try to measure these new voltage regulators, even though I don't have the correct equipment, but we can just stick a probe in there and see what happens, what we can see. The correct way obviously would be to have a correctly terminated oscilloscope and the probe adapter to attach to this tiny coax plug basically called MMXC or something like that. And other than that, I think this is fixed. So we got an ALPS mechanism from one drive, the case from another drive, the logic board from even another drive, jumbled it up all together, replaced the 74LS14 and the voltage regulators. This mod is definitely strictly optional. The drive will run fine with the original linear regulators. They might run a little hot during especially summer days or something. However, you definitely don't need to do that. If they break down, you can still get old stock 74805 and 17812s, but it's nice to have this replacement option, especially if you think that you're, for example, running this in a hotter climate and might want to take care of the cooling situation. Well, so let's grab the scope and have a poke at the outputs of these two regulators. Okay, both machines are on, the oscilloscope and the 1541. I'm gonna first check. We have 2 volts per division, so we should end up roughly here with the voltage for the 5-volt regulator. It's a bit tricky using this springy ground pin here to twist a little bit in shape to actually touch the probe here correctly. Yes, we end up exactly where we want to be. We can do some AC coupling here to get down to the 0 line and then hopefully zoom in a bit. And that's what we see here. Can try and get a closer look. And voltage peak to peak here says 30 millivolts, although this is in theory a 20x probe and my probe is set to 10x. So I'm measuring twice as much as I should, maybe? I'm not quite sure how this works. Plus, I'm probably also measuring some reflections because my oscilloscope is terminated with 1 meg ohm, and this is supposed to be 50 ohms instead. Let's check with the 12-volt line. Probing in there. See if we can get anything. Yeah, also looks interesting, let's say. Definitely some very high frequency components, and it looks different from what I get when just holding the probe like that. So it's obviously picking up noise from all the switching. I mean, even the lamp over here is an LED lamp, so there's switching noise from that and from everything in the air basically. So yeah, this here shows like 60 millivolts. So not sure if that actually makes sense. I just don't have the equipment to do this correctly, and I don't have the knowledge, to be fair. Let's go back to 5 volts per division so that we can at least determine that we get the 12 volts correctly. Yes, maximum is 12.4, so it's a little bit high maybe, I don't know. Yeah, but that looks good. Also, the noise that we're currently measuring is very high. It says 1 volt peak to peak, so I don't believe that quite. Because I also get that when I do this. So there's definitely a lot of noise already in the air. The measurement that we can do here is definitely not perfect. But it seems that this whole thing is relatively noise-free. I think that was the whole goal of this experience. I'm no electrical engineer, but I think these are good replacements if you want to have a drive that runs cooler than within normal regulators. If your regular regulators are fine, you don't have to switch them out. They are usually pretty reliable. I think this one here has some short circuit protection built in. It might be a little bit safer than the 30-40-year-old ones, but yeah. That's all I wanted to show you. We've got a working drive. It works perfectly with the replacement 74LS14 with an ALPS mechanism, with the Neutronics board basically, and the two new beautiful regulators. So if you're interested, I'm going to link to the forum thread in German. There might be an open source release at some point, but these are the prototypes, obviously. So you can't buy them yet, but they are definitely very nice, very cool running replacements for the old ones. So that's it for today. Thank you very much for watching. Share, like, subscribe, leave a comment. If you design power supplies, maybe you can weigh in and tell me something about this. Other than that, see you in the next video. Bye.